All right, welcome back. This will be covering a whole topic instead of just one question. And this topic will be the first topic that's taught in the Reactor Theory section for the generic fundamentals exam. All right, and this topic is neutrons, right? And 192.001 is a topic ID. So I looked at the question bank for neutrons and wanted to talk about the different types of questions. So what I'll go over here is more of the, not so much how to learn about neutrons and their lifestyle. I'm assuming that you've read the material and you're kind of familiar with it. Now I want to get into the how to pass the NRC exam, because that's why you're here. That's the most important thing. So let's get right into it. How to look at the exam bank and how to answer whatever questions they throw at you. So the question bank, the 2018 one on the NRC exam website has 22 questions, and 21 of them are delayed versus prompt neutron questions. All right, so if we concentrate on that, we should be successful. All right, I've broken these questions down into four different types. Four different types of the 21 total questions. Number one is definitions. The definitions of delayed versus prompt neutrons. There's 5 questions in the bank of that. P545, 845, 1145, and 1945. Those are question ID numbers for PWRs. So you'll have to know a certain few things about the definitions of prompt and delayed to answer those questions. Then there are timeline questions, which is how to properly use a timeline. We know that prompt neutrons are born at less than 10 to the minus 14 seconds. So they give us a series of questions. This neutron was born at 10 to the minus 16. Is it prompt or delayed? Or this one was born at 10 to the minus 2 seconds. Is it prompt or delayed? And you'll have to answer those. And I'll show you a little trick to get those right every time. There's 4 questions in the bank about that. P1445, 1545, 2345, and 4123. All right, the next type of question out of the 22 is going to be a likelihood. And it's going to say which neutrons are more or less likely to do something, whatever. And then you have to pick prompt neutron, thermal neutron, delayed neutron. And there's 6 questions in the bank about that. P2045, 2145, 2645, 2945, and 5023. And then the last one of the 4 types of questions for neutrons is going to be proportion. And what are the proportions of a given set of neutrons? All right? And that's just asking you, it's basically a definition question, but it's asking you that 99.36% of all U-235 fissions, 99.36 of those are prompt. So of all the neutrons born, and that means that 993.6 neutrons are in a population of 1,000 neutrons. 999.36 of them are prompt neutrons. And then this is total neutrons. And that also means that 6.4 out of 1,000 delayed. So it's basically a definition question, but you need to know and be able to manipulate these numbers. I think this is probably the best way to think of it as far as majority minority. And I believe there's 5 questions on those too. All right. So I made up a little chart. Prompt versus delayed neutrons. And the first thing in it is the vast majority are prompt. And then that's the vast majority of U-235 fissions. And that means 993.6 are prompt per 1,000. And 6.4 are delayed per 1,000. So very small minority of the total neutrons are delayed. All right, this is an important one, right? Prompt neutrons are born fast, right? Well, they're born quickly. They're both born fast, but they're born quickly, less than 10 to the minus 14 seconds after fission. And delayed neutrons are greater than 10 to the minus 14 seconds. We're going to say they're about 12.5 seconds on average. And that's an important number to remember. So both neutrons, prompt and delayed, are born fast, but the prompt neutrons have a higher energy level, more kinetic energy, right? 1 to 2 mega electron volts for prompt and 0.5 mega electron volts on average for delayed. Because of that, they're more likely to leak from the core. I'm talking to prompt neutrons. So the prompt neutrons. And the delayed neutrons are less likely to leak from the core. So this is an important thing. It's not 100% accurate, but it's pretty much accurate for the test-taking reasons, right? If you see a problem that asks what can fission a U-238 atom, it's probably going to be a prompt neutron. Oops. All right. Delayed neutrons cannot fission a U-238. They fission a U-235. The total lifetime of a prompt neutron from birth to causing a fission itself, the slowing down time and everything will be around 10 to the minus 14 seconds. 10 to the minus 4 seconds. So it's born within 10 to the minus 14 seconds, and then it slows down and gets captured at about 10 to the minus 4 seconds from birth. While it takes the delayed neutron about 12.5 seconds to one, be born, slow down, and then be captured as a fission. All right. Prompt neutrons are less likely to cause a thermal fission because they're at a higher energy rate, more likely to leak from the core. And delayed neutrons are more likely to cause a thermal fission. All right, so we use those. We use this chart to figure out the questions, right? So now the question bank. So this is the question bank off the NRC website for 2018. All right, we'll just go through them all. The first question here, I don't see any numbers. So delayed neutrons are fission neutrons that. So I know for right now that this is going to be a definition question. So delayed neutrons are released at the instant of fission. No, that's a prompt neutron, basically. Are responsible for the majority of U-235 fissions. So that isn't right because they're so small in their, those are going to be thermal neutrons. So that's not right. Have reached thermal equilibrium with the surrounding medium. That's going to be thermal. So that's not right. Are expelled at a lower average kinetic energy than most other fission neutrons. So most other fission neutrons are going to be prompt. That's true. And these are going to be, and that's going to be about 0.5 mega electron volts. So the answer is going to be D. I'll see if I'm right. Oh, delta. Cool. The next question. Delayed neutrons are neutrons that, there's another definition. Question. Delayed neutrons are neutrons that have reached thermal equilibrium in the surrounding medium. That's going to be a thermal neutron. Are expelled within 10 to the minus 14 seconds of the fission event. That's going to be a prompt neutron. Are produced from the radioactive decay of certain fission fragments. And are responsible for the majority of U-235. I like that one. So let's see. Charlie. The majority of U-235 are going to be from thermal neutrons. That's why delta is wrong. Okay, so next question. Which of the following is a characteristic of a prompt neutron, right? More definition, right? Are expelled at an average kinetic energy of 0.5 megaelectron volt? Well, no. That's going to be a delayed. And remember, prompts neutron 1 to 2 megaelectron volts. So A is not the correct answer. Is B the correct answer? Usually emitted by excited nucleus of a fission product? Maybe. C accounts for more than 99% of fission neutrons. Hey, I like that one. Remember, 99.36% are prompt. I really like that one. And like box that one in. I like that. And delta released an average of 13 seconds after the fission event. That's going to be delayed. Or more delayed. Usually emitted by the excited nucleus of a fission product are going to be more delayed. All right. And so C. I really like C. I know that's the correct answer. I'm going to mark off B and D. And we're going to see if C is correct. And look, C is correct. And next question. A neutron is expelled 1 times 10 to the minus 2 seconds after the associated fission event is a blank. All right, so this is going to be a timeline question. And it's just testing, do you know the difference between 10 to the minus 2 and 10 to the minus 14? All right, so here is 0 seconds. You do a timeline to 10 to the 0 seconds. And that's also going to be 1 second. 10 to the 0 is 1. All right, so back here it's going to be 10 to the minus 1. 10 to the minus 2, 3, 4, 5, 6, 7, 8, all the way down here, it's going to be 10 to the minus 14. This range here is where you're going to do prompt neutrons. This is that range. It's a very small range and it's very quick. So they get born here at less than 10 to the minus 14 seconds, and they die at around 10 to the minus 4. So a neutron is expelled 10 to the minus 2 seconds after it's going to be out here. Not here. So these are all delayed. Delayed. It's not going to be thermal, because they can both become thermal. All they have to do is hit a bunch of moderators. They're not going to be prompt, and they're not going to be capture neutrons. All right? So what they're doing is testing your ability to know the difference between 10 to the minus 2 and 10 to the minus 14. Don't get confused on that. A lot of people get confused on that. So that's going to be B, and that's the correct answer. All right, here's another one. A neutron that expelled 10 to the minus 6 seconds after the first fission event is a blank neutron. All right, here's another timeline question. And what do we got? We got 0 seconds, 10 to the minus 14, 10 to the minus 6, 10 to the 0, 1 second. All right, so we're at 10 to the minus 6. We're right here. And time equals 0. Well, to be prompt, we got to be in this range. And we're not, so we're delayed. So even though it's not much of a delay, we're still a delayed neutron. We're not a prompt, we're not a thermal, we're not a capture. We'll see if we're right. Looks like we're right. Next question. Which of the following types of neutrons have an average neutron generation lifetime of 12.5 seconds? So we're going to have another definition. If you remember from our chart, the generation lifetime was about 12.5 seconds. A good thing is, times 0. So 12.5 seconds are born. They're born an average of 12.5 seconds later. Then they have about 10 to the minus 6 and 10 to the minus 2 seconds after that to get captured and become thermal. So around 12.5 seconds, not only from birth, born, and then 12.5 seconds plus a millisecond or two to die. So not for a total of 24, but for a total of 12.50001 is their lifetime. But if you just remember 12.5, that'll be good enough. All right. So these will be delayed neutrons, not prompt. Prompt are born within 10 to the minus 14 and die within 10 to the minus 4. Die meaning they're thermalized and sucked up to cause another fission. Fast has to do with the energy, and thermal has to do with the energy. So let's see if we're right. B, delayed. Okay. Next question. In comparison between a delayed neutron and a prompt neutron produced from the same fission event, the prompt neutron is more likely to, yikes, assume that both neutrons remain in the core. All right. So this is going to be a definition question. A prompt neutron is more likely to require a greater number of collisions to become a thermal neutron. What do we know about collisions, right? Collisions take away kinetic energy, and prompt neutrons are born, have greater KE, so that's right? But I'm going to read the rest of them. Prompt neutrons are more likely to be captured by a U-238 at resonance energy peak between 1 and 1,000 electron volts. All right, so that should be. So remember, prompt are 1 to 2 mega electron volts. So that's a nice little distractor. Prompt neutron is more likely to. Oh, this is a likelihood question. I'm sorry. Same fission event, the prompt neutron is more likely to be expelled with a lower kinetic energy. It's more likely to be expelled from the core, but I don't know about this lower kinetic energy stuff. And delta causes thermal fission of a U-235 nucleus. It's going to be thermal neutron, so that was not right. So I'm going to say A is the correct answer. In comparison between a delayed neutron and a prompt neutron produced from the same fission event, the prompt neutron is more likely to require a greater number of collisions to become a thermal neutron. So I'm going to say A is the correct answer. A is the correct answer. Next question. In comparison between a delayed neutron and a prompt neutron produced from the same fission event, the prompt neutron is more likely to, so this is the likelihood. The prompt neutron is more likely to cause the fission of a U-238. Ooh, I like that right there, man. Be captured by a U-238 resonance frequency between 1 and 1,000 electron volts. Now remember, prompts are 1 to 2 mega electron volts. Be captured by a xenon 135 nucleus. That's not true. Remember, we like U-238. I want you to remember that. Cause the thermal fission of a U-235. That's going to be a thermal neutron. So I'm going to say the answer is A. And A is the correct answer. So if you memorize the chart, or if you just study that chart I made, you'll be able to answer these questions and not get confused at this stuff right here. 1 electron volt 1,000. Xenon 135, we never talked about that. And you know the difference between a U-235 thermal fission and a fast fission. Okay, moving on. A neutron that is released 1 times 10 to the minus 10 seconds after the associated fission event is classified as a blank, right? So this will be a timeline. And I would recommend, since there's money riding on this test, that you just do this timeline, right? 10 to the minus 14 seconds. Then there's 10 to the minus 10 seconds. And then there's 10 to the 0 seconds, which is 1 second. So a neutron that is released 10 to the minus 10 seconds, so we're right here. And of course we know their prompt neutron birth time is right here. Okay? So this is not a prompt neutron, so it's delayed. I didn't even read the answers and I know it's delayed. So it's delayed, it is not prompt, it is not thermal, and spontaneous doesn't exist. Well, spontaneous isn't what it is. Correct answer is A. In a comparison between a prompt neutron and a delayed neutron produced from the same fission event, the delayed neutron requires blank collisions in the moderator. All right, so this is going to be a definition. So blank collisions in the moderator become thermal, and is blank likely to cause the fission of a U-235 question? I take that back. This is going to be a likelihood question. So likelihood question, which is basically a definition question. All right, so delayed, born at lower kinetic energy, about 0.5 mega electron volts, compared to 1 to 2 mega electron volts on a prompt. So delayed neutron, that's what we're looking for, produced from the same fission event. Delayed neutron requires blank collisions to become thermal, so there'll be fewer. All right, because it's at a lower energy level. Thermal means it's at the same energy level as the atoms around it. So you only have to hit a couple, maybe 1 or 2, to get a thermalized delayed neutron. So there's fewer. So we're going to look up, we got fewer here and fewer here, more and more. So A and B are not correct. So we know the answer is either C or D. So fewer collisions to the moderator to become thermal, and is blank likely to cause the fission of U-238 nucleus. All right, remember prompt, fast fissions, U-238. Right. So it's less likely. It's not more. Prompt, fast fissions, U-238. A lot of questions about that, okay? If you see U-238, it's probably going to be prompt that makes it a fission. Okay, next question. In a comparison between the delayed neutron and a prompt neutron produced from the same fission event, so this is a likelihood. Comparison delayed neutron and prompt neutron, the same fission. The prompt neutron is more likely to be captured by xenon 135, cause thermal fission of a U-235. No, remember that's U-238. So it's not that one. leak out of the core while slowing down. A prompt neutron has a higher kinetic energy. It's going faster, so it's more likely to leak out. Be captured by E238 nucleus. See that resonance energy, man, that's a trick. You want a fast fission nuclear, or U238, excuse me. So not resonance energy, so delta's not correct. Captured by 135, that could be any of them, but so it's more likely to leak out of the core while slowing down. And that makes sense. So did we get that right? Let's see, good. Here's the next question. In a comparison between a delayed neutron and a prompt neutron produced from the same fission event, so this is a likelihood question. In comparison, delayed neutron and prompt neutrons from the same fission event, a delayed neutron is more likely to leak out of the core. No, that's going to be prompt. Cause fission of a U238 nucleus. No, that's going to be prompt. So now we're going to become a thermal neutron. Ooh. Cause fission of a Pu240 nucleus. So I'm going to say become a thermal neutron, right? So it's going to take less collisions. And it's going to be more likely to stay in the core. And Pu240 needs a fast fission to occur. So since there's so few of them, I'm going to say prompts are more likely to cause a Pu240 fission. And I'm going to go with C. C is the right answer. Right. So next question. During a brief time interval in a typical reactor operating a steady state near the beginning of a fuel cycle, 1,000 delayed neutrons, 10 to the 3, 1 times 10 to the 3, it's going to be 1,000 delayed neutrons were emitted. Approximately how many prompt neutrons were emitted? All right, so 6.4 delayed neutrons per 1,000 total neutrons. That's what I want you to get through your head, not many. So what it's saying is, you had 1,000 delayed neutrons. How many were, so, okay, so 1,000. This is the way I learned this in middle school. Blank of blank is blank. And times equals, right? 1,000. So we're going to go 6.4% of some number is 1,000. Okay? 6.4 times blank is 1,000. So we can find this blank by dividing 1,000 by 0.0. I'm sorry, that's 0.64. Excuse me. .64%. All right. So this will be a proportion question. And I have this right here to show me that, man, there ain't a lot. 0.0064. And divided by 0.0064. That's going to be 156,250 total neutrons. 1,000 of them are going to be delayed, and what is that? 14,625 of them are going to be prompt. And that looks like the same proportion. That's also going to be 1.5 times 10 to the 1, 2, 3, 4, 5. That's going to be this. So it's not going to be a million, a billion, or 10 billion. No, 1 million, 10 million, or 100 million. Sorry. And 1 times 10 to the 5. Is that the correct answer? Excuse me. All right, so moving on. So that's the first proportion question we've seen. It's usually going to have to do with 1,000 delayed neutrons, or 1,000 in the population. And we'll see those again here in a sec. Which of the following types of neutron is more likely to cause fission of a U-238 nucleus in the reactor fuel? Bam, that should tell you right there, man. Prompt, baby. Prompt. U-238. It's going to be a thermal neutron? No, that causes U-235 fission. So read that U-238. A prompt fission neutron beginning to slow down? Maybe. It's not going to be a delayed fission neutron. Or a fission neutron at U-238 resonance unit. It just doesn't happen often enough. B, a prompt neutron beginning to slow down. Well, you can get a loan if you like. Excuse that. It's going to be B, prompt neutron. More likely to cause a fission U-238, so remember that, okay? Next question. During a brief time interval in a typical reactor operating steady state, 1 times 10 to the 5 delayed neutrons were emitted. All right, so 10 to the 5. Approximately how many prompt neutrons were emitted? All right. Yikes. Okay, so remember, right, 0.64% of total neutrons delayed. So 0.64% of blank is the number of delayed. So you gotta find the total number and subtract 10 to the 5th. All right. So 0.64% of the total number is 1 times 10 to the 5. So 1 times 10 to the 5th divided by 0.0064. And that should be our total number. So 1 times 10 to the 5 divided by 0.0064. And that is going to be equal to 15625,000. Total neutrons. So, what is 99.36% of 15625,000 equal to? Well, you just multiply it. So you go 0.9936 times 15625,000, and that's going to be equal to the number of the prompt neutrons. So just multiply that times 0.9936, and that's going to be 15525,003. 1.56 times 10 to the 7th, or 1.5 times 10 to the 7th. And this, of course, is a proportional question. Now, does that make sense? 1.5 times 10 to the 7th. 10 to the 5 were delayed neutrons. What's that mean? So out of 15 million, out of 15 million total neutrons, about 15 million of them were prompt, and about, what is that, 10,000 of them were delayed? So yeah, not a very high number. And did I get it right? C. Yeah, that's how you do that. So I'd use this if I were you. Blank of blank is blank. Blank of blank is blank. And then instead of, you go blank times blank equals blank. So Mrs. Montemayor taught me that in middle school. Thank you, Mrs. Montemayor. Next question. A neutron that appears 10 to the minus 16th seconds after the associated fission event is classified as a blank fission neutron. So now we're getting a little tricky, right? 10 to the minus 16th. We're used to seeing, this of course is a timeline question. So I would write it out again, right? You got 0 seconds. 10 to the minus 14. What they're counting on is for you to go 10 to the minus 16. Right here, what you won't do, because you're not dumb like me, I think I did that in the past, but we're going to remember my timeline trick and go 10 to the minus 12. And we're going to eventually get down here to 10 to the minus 1 and 10 to the 0 second, or 1 second. So we know that prompts are in here. From 0 to 10 to the minus 14. Well, 10 to the minus 16 is over here. So yeah, that baby's prompt. Bam, prompt neutrons. A neutron that appears 10 to the minus 16. Now remember to look at it. 10 to the minus 16 seconds after the associated fission event is classified as a prompt fission neutron. And we know that's right. Bam, B. I didn't even have to read the other ones. I probably should have. It's not delayed because it wasn't born late. It's not thermal because that's a different definition. And it's not spontaneous. All right, so next question. During a brief time interval in a typical reactor, steady state near the beginning of fuel cycle, 4.25 times 10 to the 5th delayed neutrons were produced. So another proportion. They seem to like these. I don't. Approximately how many prompt neutrons were produced if 4.25 times 10 to the 5th were delayed? So blank. So 6.4% of total neutron population is 4.25 times 10 to the 5th. All right, so 6.4% times total neutrons equals 4.25 e to the 5. So total neutrons are going to be equal to 4.25 times 10 to the 5th divided by 0.0064. Look that up. 4.25 e to the 5 divided by 0.0064. And that is going to give you a 66,406,250. It's going to be a total. Now the rest of them, prompts, are going to be equal to 99.36% of 66,406,250. Now you just multiply that. Nope, not by 99, by 0.9936. And that's going to be equal to 65918,250. Or 6.6 times 10 to the 7. Oh, look at that. They tricked me. I almost picked B. It's not e to the 6th. It's e to the 7th. All right. Now, that should make sense intuitively because you're usually 2 orders of magnitude greater on your delayed. All right. So watch out for that, right? The answer is actually delta. The answer is not Bravo. 1.5 times 10 to the 6? No, it's not 1.5 times 10 to the 7. It's 6.5 times 10 to the 7. So let's see if we got it right. I bet you a lot of people picked Bravo. And the NRC man was very proud of himself. So that's a really good distractor. Watch out for that one. All right, in a comparison between a delayed neutron and a prompt neutron, the same vision of it, the delayed neutron are more likely to, so likelihood. So we go to our chart, and we remember that the delayed neutron does not cause fission of U-238, does not travel adjacent to a fuel assembly. I don't know what that means. I think they both do that. A delayed neutron is more likely to be absorbed by a B10 nucleus. I think that's probably true, but I don't quite remember. And leak out of the core. So a prompt is more likely to leak out of the core. Be absorbed by a B10 nucleus or travel to an adjacent fuel assembly. So I think this is going to mean that a delayed has less of a mean. All right, so I'm not going to pick B because delayed is less kinetic energy. I don't really know offhand. I haven't looked at these yet, or I looked at them a long time ago. And I'm going to have to venture a guess, meaning I've ruled out 3, and I'm not so sure on the 4th. So, will it be absorbed by a B10 nucleus? Well, B10 nucleuses are known to have big cross-sections for absorption, microscopic cross-sections for absorption. So I'm going to say the answer is Charlie. Go with that. It's not, that's a prompt for A. B is travel to an adjacent fuel assembly. So they have less kinetic energy, so they don't go as far. And a delayed neutron more likely to go further is what that's saying. All right, so B I don't like, and D I don't like. So we're going to go with C. Even though I don't really know the answer off the top of my head, and I'm going to say that the answer is C, just by process of elimination. And surely we can look that up and realize the reason why, but it also works to process of elimination. But you got to be certain. Process of elimination is rather tricky. All right. So moving on. Which of the following is a process that produces the majority of delayed neutrons in an operating nuclear power? Process that produces the majority of delayed neutrons. So definition time. A thermal neutron is absorbed by a fuel nucleus, yeah. I don't think it matters whether it's thermal or delayed. After a period of time, the nucleus fissions and releases a delayed neutron. I like it. A thermal neutron is absorbed by a fuel nucleus. The nucleus fissions. During the decay process, the fission products, a delayed neutron is emitted. Ooh, I like that one too. I like that one a lot. A fast neutron is absorbed by a fuel nucleus. After a period of time, the nucleus fissions and releases a delayed neutron. I think that's a small minority, so we'll mark that out and say it's probably going to be thermal. And a fast neutron is absorbed by a fuel nucleus. The fuel nucleus fissions. During the decay process of the fission products, a delayed neutron is emitted during the decay process. So thermal neutrons happen more often than thermal fissions happen more often than fast fissions. So we're going to mark out the fast neutrons, right? Because they just don't happen that much in U-235. Thermal neutron is emitted during the decay process, a delayed. Oh, the fission products. So the fission product daughters make more delayed neutrons because they take longer. Now remember that. This is like straight out of the nucleus. I don't think that happens that often, so I'm going to have to guess. Guess between A and B. So since I'm guessing, I'm going to go ahead and read. And that's not really a guess, it's an educated hypothesis, right? The nucleus fissions and releases a delayed neutron. So we didn't really go over this in our definition thing, but delayed neutrons are more likely to come out of a fission product daughter because you have the initial fission, right? You have a neutron. Go to the initial fission. That's going to have a fission product daughter, and maybe a neutron or two. Doesn't matter. And then you're going to have a neutron come out of here that's going to be delayed. That's where they're more likely to come from. So I'm going to go with B. The answer is B. A's not right because it doesn't come straight out of the fission. It doesn't come here. It comes here, usually. And we'll see if I'm right. B. Hey, awesome. Remember when you're guessing, man, that means slow down, really figure out why the other ones are wrong. And I just say guessing because, I didn't know off the top of my head. During a brief time interval in a typical operating steady state at the beginning of the fuel cycle, 4.2 times 10 to the 10th prompt neutrons were produced. Approximately how many delayed neutrons were produced in the reactor? So it's going to be times 10 to the 8th, something times 10 to the 8th from what we've seen earlier. But hey, we'll do it. So blank of blank is blank, right? 99.36% of total neutron population is 4.25 E10. So total neutron population is equal to 4.25 E10 divided by 0.9936. Uh, 4.25 times 10 to the 10th divided by 0.9936. It's going to be 4.2227. 4.277 times 10 to the 10th. That makes sense. They're pretty close numbers since it's 99.367. So now we go 6.4% of 4.277 times 10 to the 10th equals what? And that's going to be just multiply that by 0.0064. So they're relying on you not to do this, 0.064, when that's not correct. 0.0064 is the correct multiplier of total neutron population, 4.27 e to the 10. And that's going to give us 2.7 times 10 to the 8th. 2.8 times 10 to the 8th. That's what I got. Let's see if that is right. So I knew it was 10 to the 8th at the beginning. Remember, I didn't think it was 10 to the 9th. And ta-da, 10 to the 8th. 2.8 times 10 to the 8th. So another proportion question. So the next one. P7677, which of the following process that produces a majority of prompt neutrons in an operating nuclear power plant? A thermal neutron is absorbed by a fuel nucleus. Okay, I like it. Almost immediately, the nucleus fissions and emits one or more prompt neutrons. I like that. A thermal neutron absorbed by a fuel nucleus. Like it. Almost immediately, the fuel nucleus fissions and produces fission products. During the decay of the fission products, one or more prompt neutrons are emitted. No way, I don't like that. It takes too long to produce fission products and then have them fission. Remember, 10 to the minus 14 seconds is the birth time for a fission, for a prompt neutron. A fast neutron is absorbed by a fuel nucleus. So we're looking for the majority of prompt neutrons. Fast fissions don't happen as often as thermal fissions. That's where I'm going to go with that. So I'm going to say that those are no's, and the answer is A. So it's not a fast neutron, and that'll be what I choose, and it'll be A. Next question. The following nuclei will cause a greater loss of kinetic energy. This is the last question in neutrons. Okay? So this is the only one that's not delayed versus prompt. So what does that tell you? It's been on a recent exam, and it's a good thing to know. But you're more likely to get a question that's delayed versus prompt. And remember, this is only going to be 1 out of 50 questions on GFES. So you got a small chance of getting this one. And what I want you to know from this one is, which one of the following will cause a greater loss of kinetic energy from a 2.1 megaelectron fission neutron during a head-on collision? All right, the greater loss is going to be from the smaller thing it hits. All right, so if a little bitty neutron comes in and hits something small, that means that bang and bang, right? There's the neutron, and that one's going to go flying. And then here is the thing it hit. So this is going to lose a lot of kinetic energy if it hits something small. Now, if a little bitty neutron comes in and it hits something gigantic, well, it's going to bounce off just as hard as it did. And then this one, gigantic, won't move as much. Hardly any, really. So you're not going to lose any kinetic energy off the one you get. So we're looking for the smallest thing to hit. 2 helium-4. That's pretty small. Only hydrogen's smaller. Oxygen 16, right? I think it's going to be 7 oxygen 16. Or I think that's 8 oxygen 16, excuse me. So that thing's got 16, nuclei in them. Protons and neutrons, I should say. Zirconium 90, that means it's got 90 protons and probably 91 neutrons. So that thing's gigantic compared to oxygen, so that's bigger. And then U-235, that's going to have 92 U-235. So that's going to have a total of 235 atomic mass units in it. That's going to have a total of 90 atomic mass units. That's going to have a total of 16 atomic mass units, and that's going to have a total of 4. So the answer is going to be A. We want to hit the smallest thing possible to lose a lot of kinetic energy. We're not going to lose hardly any. We hit a U-235. And is that correct? All right. So 1 elastic scattering and 21 delayed versus prompt questions in 4 separate groups: likelihood, proportion, definition, and timeline usage. I hope that helps you in your study, and stay tuned. We'll keep going through reactor theory, and we'll make sense of it in a nice, easy way. You'll all ace your GFES exam. But for right now, that's all I have to tell you people.